Hey there, math fans. Dr. Andy Lovelace. Going to do a visual explanation of the second partial derivative test, and then I'll follow up with a proof sketch of the second partial derivative test. Some of this you don't necessarily need for the course, but it's the things that students always ask me about. So given a surface, which I have one here, the process to find and classify critical points is to find both partial derivatives, solve when they're both equal to 0. Now that's something we'll talk about in our class, reminding you about the algebra and some tips to do that well. And then after you find those points, you compute the partial second derivatives, and you compute this thing, this weird number d, or sometimes called the Hessian matrix. If d is negative, it turns out the concavity changes in some direction, and we have this thing we call it a saddle point. But ultimately, it's a thing about concavity. If d is positive, the concavity doesn't change, and that means it's either a local max or a local min. You figure that out by going back over here and figuring out, what does this tell me? Well, this tells me it's concave down in the y direction. So in this case, it's got to be concave down in all directions, so it's got to be a local max. In your head, you should be thinking concave down, local max. That's the process. So the process is this computational thing. You plug in these numbers. That's it. So that's how most of what students get out of that. I will do another example in a second, but I wanted to show you some visuals. So here is the surface. I'm actually standing above the point, -3, -9, and you can actually see it's a maximum. The other critical point, 0, 0, is, I'll move over to it, 0, 0 is over here, and it's a saddle point. You can see that. But ultimately what we're doing is we're measuring the concavity. So let's go back to that first point, and I'm going to show you the contours, and I'm going to show you a bunch of the numbers being computed. So let's go to -9, -3. And now I'm going to show you some visuals, and then we'll do another example. Okay, so there we go. There's the contour map on the ground, and there's the numbers. So I got this just so you could see all the numbers computed. Let's move this over so you can see it. So there we are. We're standing at that point, and I actually made it so I could do the concavity in all directions. So I have this vector I can move around a bit. So you can see it's concave down in all directions. There's some places where it's pretty small, but it's still concave down in all directions. That's what's happening. So the d, this d thing we're computing, this 18, whenever it's positive, it means it's the same concavity in all directions. It doesn't change. It's not a saddle point. And the fact that it's -27, the second partial in the x direction, and -1 in the y direction, that means it's concave down in all directions. If you go back over to this other point, then you can see the concavity changes. In this direction, it's concave up. And so that's what we're seeing. So that's really what we're doing, is we're looking in all directions. Now in this course, we only are looking in the x and y direction. But ultimately, to prove things like this, you have to look in all the directions. So that's it. We're spinning around. We're saying it's concave down in all directions. And then we're going to the other point. We're computing these things. D is negative. That means the concavity is changing. That's at this 0, 0. So I've been having fun making these visuals. I hope that sort of helps you see it's concave up. Now it's concave down. So I just thought I would show you another one. So the other example down there at the bottom is a little more exotic, simply because it has 6 critical points. And I would encourage you to try to find them. They're actually not that bad to find. But anyways, let's look at it. Here's this one, and let's go stand at some of the critical points. So here's one. Is that the one we're at? We're at the one where it's positive. So we're actually standing here. So let's go there. And let's go to the same spot. So I want this to be 1, this to be 0. Okay, now we're standing on there. I'm going to just send it spinning for fun. So we're going to do A little bit of adjusting here. Let's send it spinning. Nice. Let's send this one spinning. And as it spins, you can see it's concave down in all directions. So for this one, if you plugged in the D, you get a positive 32. Again, that doesn't tell you what it is. It just tells you the concavity is the same in all directions. And the fact that both the second partials with respect to x and y are negative, it's concave down in all directions. And you can see that in the 3D picture, and you can see that in the numbers that we would have gotten. Let's go to another point. How about over here to when y is -1. And we'll do the same. Let's move this over here. I made it so I can move all these. Also concave down in all directions. Now let's go to this critical point. There's actually a critical point right here in the middle at 0, 0. So let's go there. And you can see it's concave up in some directions and concave down a different direction. You can see that the D is negative. So that's what that D represents. It gives you this information. Whenever it's negative, it's a saddle point. Let's go back here to this point. Let's see. This is when x is, I believe it's 4/3, 1.3, about. And you can't see it's back there. I'll make this go a little faster, make this one go a little slower. And there we go. That one's concave up in all directions. D is positive, the mixed partials are positive. There we go. And then there's two other saddle points. There's a saddle point here. Notice the D is a -30-ish, and over here the D is negative. That's what those numbers are. So if D is negative, the concavity changes in some direction. If D is positive, it's either a local max or min. In order to figure that out, you got to look at the other numbers. That's it. We're really tracing concavity, just like we did in one variable calculus. It's just there's more directions to look. All right, I hope that gives you a little more insight into what it's saying.